All right, ladies and gentlemen. Well, hello, and I'm excited to get going here today. We are going to be opening up a brand new chapter, chapter 6. And in this chapter, our main focus is going to be on the concept of vectors and parameters. And things are going to look a little different in this chapter, and we're excited to get going here. So in this entire section in general, our ultimate goal is to be able to apply the arithmetic of vectors and utilize vectors to actually solve some real-world problems. In this video, we're going to start really small. We're going to define what a vector is. We're going to talk about what a scalar is, a little bit about magnitude, initial points, terminal points, and then we're going to be able to write a vector in component form. All right, so we're going to start real slow to get things going. So first and foremost, what in tarnation is a vector here? Well, I'll give you the first real kind of mathematical definition behind it all. But simply put, when we are talking about a two-dimensional vector, all right, honestly, a two-dimensional vector is an ordered pair of real numbers, right? It's really just an ordered pair. And that ordered pair kind of talks to us about direction, okay? Kind of tells us what that direction is. And we call this direction or this ordered pair component form, and that is what you see here. And so this kind of arrow-shaped parentheses, that is component form of a vector, in which that a, or the quote-unquote x-coordinate, what that is telling us the horizontal direction, either left or right. And then B, the y-coordinate, if you will, is telling us the vertical direction, either up or down. Now, when we are talking about a vector in general, we have to understand that a vector has two things, and this is so critical in you moving forward in higher level mathematics, is that a vector has both magnitude and the direction that I was just talking about, all right? So it has two different things. It has magnitude and direction. If you are wondering what magnitude is just simply size. It has size and direction, if you will. The magnitude, we always denote it with this kind of lowercase bolded v that you see right in here, okay? That is the length of the quote-unquote vector, all right? The length of the vector, right? And then the direction, as we talked about before, was with our component form that we have. And then last but certainly not least about our vector discussion, we also have a zero vector. A zero vector is just a vector that has no magnitude and no direction, or no length and no direction here. So let's take a look and kind of show what this vector is. A vector, if you will, kind of is an arrow. I hate to say it. That's really kind of what it is. It's an arrow on a coordinate plane. If we're going to break it down super simply, that's what you're going to see. A vector is an arrow on a coordinate plane. But if you imagine, for example, and let's say, for instance, that this point right here is the origin, and you had a point, an ordered pair, a comma b, we would all agree that I go x in the x or the horizontal direction a number of units. And then to get to this ordered pair, I would then have to go b number of units up or down, but in this case, going to be up. And that is what this component form actually represents. So let me kind of just show you real quick with a basic kind of understanding. Let's say, for instance, that I change these into numbers. So let's say, for instance, I said that this was 3, 2. So that means that this vector right here would have a component form of 3, 2 from the origin. I went 3 units to the right and 2 units up, right? I went 3 units right and 2 units up. Well, now let's say, for instance, that I went ahead and said, what if I asked where was the component form, or where would the vector be for 3, -2? So now that is 3 units right and 2 units down. And so if that's the case, I then would come out here and I would still go my 3 units right and my 2 units down, and that would leave me at a vector at 3, -2 at the ordered pair of 3, -2. So hopefully that makes sense so far of what a little bit more of the basics of our vector is. As we close up shop on this video, all right, I'm going to be discussing about what we call the head minus tail rules, all right, the head minus tail rule. Okay, so if an arrow has an initial point, all right, and it has a terminal point. So let's back up to what my previous examples were. My initial point for these vectors that I showed up here would have been the origin at 0, 0. And then what I would have shown in the terminal point would have been 3, 2. It would have been 3, 2. And so that is why we have a initial point here and a terminal point here. Okay, so now the head minus tail rules for vectors. If an arrow has an initial point, we're going to call that x sub 1, y sub 1, and a terminal point, we're going to call that x sub 2, y sub 2, then it represents the vector x2 minus x1, comma y2 minus y1. If you think about what I showed you up top, that makes sense. 3 minus 0 was 3. That is why we had a vector of 3 for the x coordinate. 2 minus 0 is 2. That is why we had a 2 in our y coordinate. So let's take a look at a real quick example of how we can show that arrows or vectors are equivalent using this kind of identity right here, this rule called the head minus tail rule for vectors. So if you think about what's going on, we can see here that we have the distance, all right, if you will, of these vectors are going to be the same. Because if you see that we have a vector, and I'm going to go ahead and draw a vector on out real quick. So we've got ourselves a vector at -4 and +2, right? So at -4, +2, and then that will go to -1, +6. I'm going to put our 6 up here, and I'll put my -1 here. So that means I'm going to have my initial point at -4, +2, my terminal point at -1, +6, and that would be my vector rs. And so we're going to write that just like this, vector rs. And then it says we also have another vector. It's going to be pq. And vector PQ is going to be at 2 and -1. So we'll have our initial point there at 2, -1. And then we are going to have a terminal point at 5 and +3. So it's going to be up here. And we're going to call that guy vector PQ. And so in order to show that these are equivalent, we can go ahead and use that head minus tail rule. So we can go ahead and show that we have -1 minus a -4. So we have -1 minus a -4, comma 6 minus 2. So that means that we have -1 plus 4, of course, is going to give us a +3. 6 minus 2 is going to give us a +4. And that is going to be equal to vector rs. So now we can do the exact same head minus tail rule with our vector PQ to go ahead and to see that they are equivalent to one another. So we can go ahead and take 5 minus 2, head minus tail, and 3 minus a -1. And of course, we still do get the exact same thing of 3, 4, which is also equal to vector PQ. And that is how we can kind of show length of a vector and direction of a vector, and to show that they are equivalent by using our head minus